Hello friends, I welcome you on my channel Engineering Mathematics DJ Ganit. In this lecture, we are going to discuss how we can approximate binomial probability distribution using normal probability distribution. So sometimes in binomial probability distribution, if number of trials are very large, then it is difficult to calculate probabilities using binomial distribution. So in those type of cases, we can calculate binomial probabilities using normal distribution as an approximation if it is possible. So the normal distribution can be used to approximate binomial distribution when the number of trials n is very large. So if n is very large, it is difficult to calculate probabilities using binomial distribution. Fortunately, the normal approximation is most effective in this type of cases. So whenever we have large number of trials in the binomial probability distribution, we can use normal probability distribution to calculate binomial probabilities. So if x is a binomial random variable with parameters small n and small p, as we know n is the number of trials in binomial experiment and small p is the probability of success, then capital Z equal to x minus n into p over square root of np times 1 minus p. This new random variable is approximately a standard normal random variable. So this result says that we can approximate binomial probability distribution using standard normal probability distribution. Now it is not always possible, or it is not always that we will get the exact answer as in the case of binomial distribution. But if certain conditions are satisfied, then we can apply normal probability distribution to approximate binomial probability distribution. So as a rule of thumb, we can say that if n into p is greater than 5 and n into 1 minus p is greater than 5, then this approximation is good to approximate binomial distribution. Some authors consider, instead of greater than 5, some authors consider n into p greater than or equal to 10 and n into 1 minus p greater than or equal to 10 for this type of approximation. So we will remember this rule of thumb, that if n into p is greater than 5 as well as n into 1 minus p is greater than 5, both are required. N into p is greater than 5 and n into 1 minus p is also greater than 5, then the normal approximation is good for binomial distribution. Now whenever we are applying normal distribution to approximate binomial distribution, we have to take care of certain things. Suppose capital X is a binomial random variable which can be approximated by normal random variable. Then if I want to find out probability of capital X equal to small x, then here this small x is integer value and we are approximating discrete binomial random variable using continuous normal random variable. And as we know that if our random variable is continuous, then probability that capital X equal to x is 0. So we have to take care, if we want to approximate this probability that capital X equal to small x, then we have to consider this probability capital X equal to small x as the area of the rectangle with center this small x under the normal curve. For example, suppose I want to calculate probability that capital X equal to 7, then I will consider the rectangle with center X equal to 7 over this interval 6.5 to 7.5. So this probability that capital X equal to 7 is nothing but area of this rectangle under the normal curve, and we know that area of this rectangle under the normal curve is nothing but probability that capital X lies between 6.5 and 7.5. So we are subtracting 0.5 from 7 and we are adding 0.5 from 7. So this is known as continuity correction. Because we are approximating discrete random variable using continuous random variable, we have to apply continuity correction while we are approximating discrete random variable by continuous random variable. So for continuity correction, we will assume that probability that capital X equal to 7 is nothing but area of rectangle shaded as shaded by these red lines. So probability that capital X equal to 7 is nothing but area of the rectangle over this interval 6.5 to 7.5, and this area we can calculate using normal distribution that we will discuss in the next lecture. So probability that capital X equal to 7 is nothing but the area of the rectangle under normal curve as shown in this figure, and that area is nothing but probability that capital X lies in between 6.5 and 7.5. So this modification is called continuity correction. In general, probability that capital X equal to small x is nothing but probability that capital X lies between x minus 0.5 and x plus 0.5. For example, suppose we have this normal curve and suppose our point X is somewhere here. So probability that capital X equal to x is nothing but area of the rectangle, area of this rectangle. This point is x minus 0.5 and this point is x plus 0.5. So area of this rectangle is nothing but probability that x minus 0.5 less than x plus 0.5. Similarly, we can calculate this type of probabilities using normal distribution but by taking proper continuity correction. Suppose we want to find out probability that x is greater than 7, then I have to consider this type of continuity correction. Suppose I have 7 here and I require the probability that x is bigger than 7. So first I will consider rectangle or box around this 7, and this distance we will always consider as 0.5. So this is nothing but 6.5 and this point is nothing but 7.5. Now I require the area or I require the probability that x is greater than 7. So x is greater than 7 means x is greater than or equal to 8. So I have 8 somewhere here. X is greater than or equal to 8. So I will consider for 8, I will consider this area. This is 0.5 and this is 0.5. So suppose this area is for x equal to 8. This point is 8, this point is 8.5. So this rectangle is for x equal to 8. this one is for x equal to 7. So probability that x is greater than 7 is equal to probability that x is greater than or equal to 8, because x is a discrete random variable. So x is greater than 7 means x can take values 8, 9 and so on. Because x is a discrete random variable, it can take only integer values. So therefore these two are equivalent, or these two are equal. Probability that x is bigger than 7 is equal to probability that x is greater than or equal to 8. Now probability that x is greater than or equal to 8 is nothing but, if you observe here, then area of this rectangle is nothing but probability that x equal to 8. So this box or this rectangle includes x equal to 8, and we are starting from x equal to 8. This probability is nothing but probability that x equal to 8 plus probability that x equal to 9 and so on. So we have to include x equal to 8. So if we want to include x equal to 8, we have to start from this. This is the left hand side of this rectangle. So if we want to include x equal to 8, we have to start from x equal to 7.5. So area to the right of x equal to 7.5 is required area. So probability that x is bigger than 7 is nothing but probability that x is bigger than 7.5. So in this way, whenever we want to find out this type of probabilities, we will consider the rectangle surrounding that point, and from that we will have the idea. Suppose I want to calculate this probability that x is strictly less than 7. So x is less than 7 means, because x is a discrete random variable, this is equal to probability that x is less than or equal to 6. Now x is less than or equal to 6, that means I have to consider rectangle surrounding x equal to 6. So suppose this is 6 and this continuity correction is 0.5, so this point is 5.5, this is 6.5. So this is the rectangle corresponding to capital X equal to 6. Now I require probability that capital X is less than or equal to 6. So I have to include x equal to 6. So this rectangle is the area for capital X equal to 6. So if I want to include x equal to 6, I have to go up to 6.5, because this is the right boundary of this rectangle. So this is equal to probability that x is less than 6.5. So in this way we have to be careful while approximating binomial distribution by normal distribution. We always have to add continuity correction factor. So in general, suppose I want to find out this probability that capital X is less than or equal to x, then suppose I consider rectangle with center x. So this point is x minus 0.5 and this point is x plus 0.5. Now I require the area to the left of x. So area to the left of x. Before that, area for capital X equal to x is nothing but area of this rectangle. So area of this rectangle is corresponding to capital X equal to small x. So here we require probability that x is less than or equal to x. That means we have to include x also. So to include x, we have to go up to this point, because this rectangle corresponds to probability that capital X equal to small x. So we have to include this probability also. So we have to consider probability that capital X is less than or equal to x equal to probability that x is less than or equal to x plus 0.5, because this probability that x is less than or equal to x is nothing but probability that capital X equal to x plus probability that capital X equal to x minus 1 and so on. So to include this probability means we have to include this rectangle. So the right boundary is x plus 0.5, so we have to consider x plus 0.5. Similarly, suppose we require this probability that capital X is greater than or equal to x. That means we are considering this type of probabilities. Probability that capital X is greater than or equal to x. This probability that capital X is greater than or equal to x is nothing but probability that capital X equal to x plus probability that capital X equal to x plus 1 and so on. So we have to start from this probability that capital X equal to small x. So we are going to the right of x and we have to include this probability. So this probability means area of this rectangle. So in that case we have to start from lower boundary, that is x is greater than or equal to x minus 0.5. So this either we can remember these two things or we can easily decide for particular values of x by considering the rectangle surrounding that value of x. Similarly, we can add continuity corrections for another probabilities like this probability that x is greater than 8 and x is less than or equal to 9. So because x is a discrete random variable, 8 is less than x is equivalent to 9 is less than or equal to x. So I replace 8 less than x by 9 less than or equal to x. So this is nothing but probability that capital X equal to 9, and that we have discussed. This probability is nothing but probability that 9 minus 0.5 less than or equal to x less than or equal to 9 plus 0.5, that is 8.5 minus x less than or equal to 9.5. So simply we are considering the rectangle with center 9 and with this length as 0.5. So this point is 8.5, this point is 9.5. So area of this rectangle is nothing but probability that x equal to 9. Now we consider probability that 10 is less than or equal to x less than or equal to 11. So if we consider this x is greater than or equal to 10, so suppose we consider the rectangle with x equal to 10. So x is greater than or equal to 10 means we have to start from this side 9.5, because x is greater than or equal to 10. This is equal to probability that x equal to 10 plus probability that x equal to 11 and so on. So we have to start with probability that x equal to 10, and this probability is nothing but area of this rectangle. So we have to start from this side, lower boundary 9.5. Okay, so it is probability that x is greater than or equal to 10 is nothing but probability that x is greater than or equal to 9.5. Similarly, probability that x is less than or equal to 11. So we have to start from probability that x is less than or equal to 11 is nothing but probability starting from 0 to probability that x equal to 11. So we have to include this area. So if we consider the rectangle with center x, this is 11.5, this is 11 minus 0.5, that is 10.5. So we have to go to the left side of 11, but this rectangle corresponds to x equal to 11. So we will consider left side of this boundary. So we require x is less than or equal to 11. So we will go to the right of 11.5. So that is nothing but probability that x is less than or equal to 11.5. So in this way we have to use continuity corrections before we calculate probabilities using normal distribution. So I hope you understand this lecture. In this lecture we have discussed when we can apply normal distribution to approximate binomial probability distribution. So we will remember this rule of thumb that if n into p and n into 1 minus p both are greater than 5, then we can apply normal approximation to the binomial probability distribution. And to apply normal probability distribution, we have to understand this continuity correction. So continuity correction is required to calculate probabilities using normal probability distribution. So I hope you like this lecture. Thank you very much.